Welcome to the ATZ-Webinar about acoustic virtual product development in the automotive industry. My name is Philipp Oberdorfer. I am physicist and manager technical marketing in the German Comsol office located in Göttingen. I'll be moderating this webinar today, and I would like to take the opportunity to thank ATZ and Springer Professional Verlag for the opportunity to present this webinar today. So let me please introduce you to the speakers, who are Mats Herring-Jensen, who joined Comsol in 2011, and he's the technology manager for the acoustics products. Mats has a PhD in computational fluid dynamics from the Technical University of Denmark. And before joining Comsol, he worked in the hearing aid industry for 5 years as an acoustic finite element expert. Good afternoon, Mats, and thanks for joining us.
Thank you, Philipp.
And then we have Michael Donchev, who joined the Amvoid Group as Chief Operating Officer in 2020, and he leads the operating businesses of the automotive, consumer, and professional audio divisions. One of Michael's priorities is the integration of Amvoid's validated methodology into digitalized customer development processes, and prior to joining Amvoid, he worked at Harman International for almost 20 years. Hello and welcome, Michael.
Hello, Philipp. Hi.
And last but not least, we have Dr. Alfred Swobodnik, who is the president and CEO of the Amvoid Group, specializing in providing consulting services and innovative technologies for automotive, consumer, and professional audio, as well as the developer of the overall Amvoid methodology. Alfred is an entrepreneur, thought leader, engineer, and scientist, and he has been researching for 30 years in the areas of multiphysics and virtual, as well as computational acoustics. And prior to founding Amvoid in 2011, Alfred spent 5 years with Harman International likewise. Good afternoon, and thanks for joining us, Alfred.
Thank you very much, Philip, and good afternoon, maybe good morning or good evening to the attendees wherever they are at the moment.
Right. Before we start, just a little bit of housekeeping. You can submit your questions via the GoToWebinar control panel during the whole event, so please feel free to ask anything. And you should be able to download the slides also via the GoToWebinar control panel in the handouts section. And this webinar will be recorded, and the recordings will be made available for you soon. So let's start. Audio technologies and acoustics are becoming increasingly important in the automotive development. And we have engine noise, we have legal requirements, there are customer wishes, the possibility to work with noise cancellation or compensation. We have legal requirements, I already mentioned that, and we have a completely different situation when we are talking about electric cars, for example, which is of course a trending topic today. And as in almost all other industries, the virtual product development is a tool that is of increasing importance because it allows for analysis, predictions, and optimization of things that are really hard to measure, for example, and all that while saving costs at the same time. So in this webinar, you will learn about the advantages and opportunities of acoustic virtual product development and how to use simulation sustainably, and a lot more, of course. And we will start by handing over to my colleague Mats, who is going to introduce you to the Comsol multiphysics simulation software and the acoustics module. And after that, we will hand over to the colleagues from Amvoid, who are going to present to you the Amvoid simulation process technology and the integration and dissemination from a technical and especially also from an organizational point of view. And after that, we will discuss your questions in the Q&A session. All right, so having all that said, I will turn off my webcam now. And Mats, you should be able to switch the slides now.
Let's see.
Perfect.
Yes, it works. Thank you, Philip, for the introduction. I will give really a brief just a really quick and brief introduction to the acoustics capabilities in Comsol multiphysics, just with a few slides, and then I will leave most of the time for Alfred and Michael to discuss. So I have this single slide about the acoustics module, and I really like to think of our acoustics module and acoustics products as being multi-purpose, multi-physics, and multi-method. So 3 times multi. By multi-purpose, I mean that we have the technologies and the physics, we call them, to model all types of acoustics. So we not only modeling acoustics inside of a car solving the Helmholtz equation, for example, but we also have formulation of the governing acoustic equations when you have a background flow, when you are modeling acoustics in small devices with thermoviscous acoustics, and so on and so forth. So a lot of various implementations of the governing equations for acoustics that have more or less details depending on the situation. And all that is packaged together, and you can couple many of these formulations together also. Then whenever you are, or in many cases when you're talking about acoustics, it's also multi-physics. So, and these capabilities are some of the very strong points of Comsol, obviously. So we have capabilities for modeling vibroacoustic systems, acoustic structure interaction. We have capabilities for modeling piezoelectric materials. You can model the background flow for convected acoustic simulation. We have various models for modeling porous materials, going from the full details of solving Bose equations to simplified what we call pressure poroacoustic models, or they're also known as equivalent fluid models. And then, of course, also when dealing with loudspeakers, it's important to model electroacoustics. So you can model loudspeaker drivers fully coupled, including all the details of the magnetic fields, electric currents, two-way coupling via the Lorentz force to structures, and two-way coupling again to the surrounding air. Or you can choose to do a lumped approach, modeling parts of your speaker as a lumped Thiele-Small system, for example. To model all these things that I've talked about here, and also being able to handle the large range of frequencies that you have in the, for example, in the audio range from 20 Hertz to 20 kilohertz, say, then the acoustics module also uses a multitude of methods to solve the equations. So the backbone for most of the applications will be the fine element formulation of the equations. We also have boundary element formulations. You can model hybrid fine element boundary element problems with fully two-way coupled FEM-BEM systems. That's, for example, shown in the image to the right here, where you have a loudspeaker. The inner part of the loudspeaker is modeled with fine elements, so the air inside of the loudspeaker, the cabinet is a solid, the driver is modeled with shells, and the outside acoustics is modeled with boundary elements. And we have a plenitude of multiphysics couplings here, coupling the vibrating structures to the BEM domain, to the FEM domain inside, and the FEM domain to the BEM domain in the port of the loudspeaker. We have ray tracing capabilities for modeling high frequency acoustics. And then we are intensively working on time domain simulations using the so-called discontinuous Galerkin or time explicit formulation or method for the governing equations. Can be used for ultrasound simulations, for example, in flow meters. That was one slide with a lot of information in it. Let's just look at a few more examples still. Okay. Yeah, here we go. So I mentioned modeling transducers. And here's one example of a fully or full electrovibroacoustic model of a transducer, a loudspeaker driver, where we are modeling the magnetic system, the pole pieces with some nonlinear iron materials. We have voice coil, cone, dust tap, etc. So that's one thing, of course, when you start looking from the transducer side. Then when you are working, in this case, today we're talking a lot about car cabin audio. Then how do you want to include your speaker into the cabin of the car as the source? You have two different choices. You can, let's start at the right maybe, for example. So in the lower frequency range, you will be typically doing a full wave method. So could be fine elements. We can see here we have a speaker, a mid-range speaker sitting in the door of the cabin. And you can model your cabin using the full in the frequency domain, for example, up to say 2-3 kilohertz. With our new latest solvers, you can actually go quite high up in frequency, 5-6 kilohertz actually, and do the full wave method. But probably for efficiency, you will tend to maybe stop at 3 kilohertz. And in this case, you can model your speaker as a lumped model, or you can actually integrate the full fine element model of the speaker in the car. You can also, model the car door and the coupling between the speaker and the car door. You have volumes inside of a car door. You can extend the complexity as much as you want. Boundaries in the car can be modeled with impedance boundary conditions, or you can actually model, for example, foams with porous materials. When you move to higher frequencies, you will then typically switch to the ray tracing method. And in this image here, I'm actually showing a hybrid fine element ray tracing approach where the rays are not released from a point as you do in classical ray tracing, but they're actually released from a surface. And the surface is a small volume that surrounds the location of the tweeter close to the windscreen. And in this small domain, we're actually solving the full wave problem with fine elements. So that's a more advanced FEM ray tracing, but you can also use classical ray tracing. So these are the typical tools and the tools that they use. Some of these tools, or both the tools they use at Emvoid for modeling car cabin acoustics. A final little example here. Philip, you mentioned vehicle electrification, and I just had this slide from a webinar or a Comsol day we had the other day. And in this case, it's a modeling of an electrical vehicle warning sound. So there are certain regulations that electrical vehicles, when they move very slowly, they should emit a sound so that pedestrians can hear them. And in this case, we have a small transducer sitting below the electrical car, and the small domain is modeled with fine elements with a detailed model of the transducer, and then the exterior acoustics is modeled with boundary elements in this case. I thought it was a pretty cool image here. Yeah, my final slide, I just want to invite you all to go to our homepage if you want to learn more about the multiphysics and acoustics capabilities of Comsol Multiphysics, comsol.com. Here's a in this page here, I've clicked in on the Acoustics Module product, where you have details about all the capabilities in the product. We have also a great blog, great user stories, a lot of nice information on our homepage. So I really invite you to take a look there. This was really just a short introduction from me, and now I want to hand over the scene to Michael. I think he's the one starting now. So, Michael.
Correct. Thanks, Mats. And Michael, I will make you keyboard and mouse, give you keyboard and mouse access. So you should be able now to switch the slides.
Okay, perfect. Yeah, I am. Yeah, thank you, Mats. I hope you guys can hear me. So
yes,
perfect. Good. I would like really to lead you through the first part of our presentation, which is structured, as you said already, Philip, in these three topics: the Emvoid simulation process technology, really talking here about the automotive audio version, and then looking at the integration and the dissemination from a technical point of view, but also really then from an organizational point of view. So let's start with the Emvoid simulation process technology. So here I would like really to start with the use cases and the applications of our customers. Most of them have been already mentioned by you. So beside an outstanding sound experience, considering the entertainment, there is more and more, or there are really more and more requirements for the automotive audio system in terms of infotainment, talking about really a clear car communication. So the vehicle acoustics from an NVH point of view, simply to improve the ride comfort with ANC, but also, as mentioned, important legal requirements for AVAs, for the learning systems, but also then really the e-calls. So, and giving an overview, first of all, what is the MVOID methodology? So the fundamental principles of our methodology is to virtually optimize the acoustic performance of products and systems in an early phase of the product development process. So really to create a decision base for product development across the hierarchy at the customer, and to lay then the foundations for the further development. Our simulation environment represents a fully digital development environment for automotive audio systems, but also develops products with acoustical properties in the virtual space by multidisciplinary simulations. And thereby we are integrating the engineering disciplines like the multiphysical engineering analysis, digital signal processing, sound tuning, psychoacoustic, and the subjective evaluation, which is extremely important, but also really the binaural audio. So on a tier level, in regards of our methodology, we are starting on the component level, really talking about the loudspeakers, and ending up on a system level by achieving the digital twin. So thereby starting, as I just said, really on a loudspeaker level. Then in the next tier level, we are integrating the enclosure, and then modeling these tools then really in the car cabin. And this represents then the first phase, which is called really the virtual prototyping based on a Comsol model. After that, we are continuing then our methodology with a level 4, the virtual tuning, a level 5, really the auralization, and a level 6, talking about the matching between the virtual model, so the digital twin, towards the physical car. And again, this represents then the virtual system engineering of our entire process. So the question is for sure now, how does this fit into the product development process from a customer perspective? Let's assume in this case a really simplified, because otherwise we could spend hours really talking about the product development process and the important milestones. So I tried really to simplify this on a concept and a pre-development, a design and development, and on an SOP. So at the beginning, there is target definition coming from a car line where clear expectations are communicated top down, and the audio engineering team, they are really then defining the architecture based on their experience and assumption. So this is entering then a specification on the customer side, going through an RFQ process, nominating the suppliers, and then having really based on these requirements the product development phase by going through a B sample, a C sample, D sample, the entire industrialization, the rollout of the different models, and then through the product launch into the SOP. So as I said, I wanted really to simplify this, and therefore I just took out one important milestone, which is the first audio experience. So this means from the day one where the architecture was defined, time is passing by towards a C sample where a first audio experience can be realized on the OEM side. Now I would like really to present you the product development process based on the digital reference, the digital twin, again having the same phases. And here we are starting the modeling based on the functional DMU in the early phase, the earlier the better. So within the audio architecture, doing then the virtual tuning, and here creating then the first virtual audio experience, followed by the digital reference. So what does this mean? And this is for me an extremely important information I would like really to share with you in regards of the time. So here we have the customer feedback that our customer, they need 10 to 15 working days really to create the digital reference. So, and based on this ideal speaker with an ideal environment, so the concept model, this is then the time what we really can ensure, or within that time also the first virtual audio experience. And furthermore, again, we are enriching the experience and assumptions in an architecture and for the audio team. So really with the simulation and the auralization. So we have really facts, we have data, we can experience how the sound could then really be experienced later on in the car. So, and ideally, this would be then available prior towards the concept approval milestone to have, in this case, the most efficient impact on the product development process. So afterwards, we are then continuing with the digital twin by integrating the more and more available refined data and the refined informations. And important is not only, so from my experience, just really the definition. It is really important to have control over the entire product development process in terms also about the change requests. And here our methodology is giving a clear reference points to our partners, our customers. So really making the right decisions on the change request, which will occur for sure through a product development process, and also really considering a product industrialization by finally passing the product manufacturing validation and ensuring that the target and the performance which have been defined at the beginning will be then also realized at the end. And again, I want really to underline the statements made already. Here we are not talking about only a sound experience. It is really also legal requirements which needs to be fulfilled today and more in the future. So, and therefore it is important to have this reference going also through a product manufacturing validation. So, and finally having then the product launch and entering then the SOP. Our vision is to have a prototype free, so a physical prototype free product development, and really replace the prototype or the physical prototypes with the virtual ones. And looking now, really breaking this down towards a strategy, a business plan, this is already realized from our customers and partners, really with reduced physical prototypes to improve their product development process. So let's talk about the integration of the Amvoid simulation process technology into the OEM product development processes, because this is a must-have to have the most efficient way and also then the involvement of the needed parties. So again, the simplified process, and to really just zoom here into the concept, pre-development, design development, and the SOP. So we are starting, or we are adding really our milestones into existing process by simply the use of existing tools like Comsol, so that the implementation is really on a most lean level. And again, starting with the modeling, going through the virtual tuning, the auralization, the digital reference, and the digital twin. So before we are going into the reduced C-sample phase, we are also providing then our level 6 in regards of the measurement system, so that a comparison can be realized, and finally the product manufacturing validation can be passed. So now I would like really to close my loop of the presentation in regards of the MVOID tier levels representing our simulation process technology. And as mentioned already before, so we are starting from a component level, going down towards a system level. And in this case, we're starting with the tier level 1 of the multi-physical modeling of the loudspeakers, then continuing as presented by adding the enclosure. This can be here, for example, a door module from a tier 1. And then the tier level 3, where we are including also the listening space. And this is also the tier level 3 represents most of the time the level where the OEMs are starting with. And this is not a sequence way to say, okay, you have to go from 1 to 2 to 3. It can be that now we are finding out, or our customers are finding out any issues which needs to be solved, so that from a level 1 there could be the need going back towards a level from a level 3 to a level 1 or 2, really fixing the issues, so that at the end of the day the final result can end up into the virtual tuning, can be can really go through the auralization, so that this experience will be then available. And as already mentioned, our tier level 6 representing then the physical testing, meaning here we are really comparing the physical car with the virtual digital twin. So our summary is that digitalization of the product development process, it is not a mega trend. This is really a must-have. So in other words, we are really talking here about the digital transformation. So, and here we are going through the milestones of the virtual tuning, the virtual auralization, so having really the first experience, the digital reference, ensuring that all requirements will really be part of the specifications, and therefore also have the foundation for the right and the most efficient product development. Then creating really the digital twin as a reference for all the activities right afterwards, and finally really passing the manufacturing validation. So, and with these milestones, we are providing the benefits of a clear design to target. And the target, as said before, is not having the best-in-class sound system only. The target is also legal requirements, which needs to be considered in future, but also really the performance defined by the engineering. So, and this is then also really basing then on an increased product and production quality, because from an entire business case perspective, this cannot be ignored in regards of customer satisfaction and really having the best-in-class car audio system on the market. And we are reducing thereby the product development time and optimizing the cost and weight. So this is only one half of the story. So it is also important having really the system responsibility clearly in mind and having the focus on that. So that in this case, we are bringing together all departments, so really design, NVH team, simulation, D&E team, manufacturing, so that based on the now available data and the experience through the auralization, they can make the right decision for their changes in their system. And on the other side, talking really about the suppliers, so that having more and more suppliers involved in the audio system, there is also important really to bring together the the transducer team, the team from the amplifier, where even here different responsibilities are on the OEM side, so that the entire system responsibility for the automotive audio system will be then ensured over a lifetime. So we created a methodology to transfer really the first ideas of a pre-development of acoustics and sound design by a multidisciplinary simulation model to the real world. So thereby following really the V model, but in this case, our methodology is really the MVET methodology, is shortening the time and delivering the benefits I just really presented to you. So this is my part of the presentation. Thank you very much for your attention. And now I would like really to hand over to you, Alfred.
Thank you
very much, Michael. Oh, sorry.
I'm sorry. Just before we forget that, we prepared a poll question, and maybe this is the right time to start that poll question.
So we're at the moment more or less on yes, about like 75%, but only we are waiting a little bit longer because 50% have voted just now. We give it a little bit more time, and I will give you the final result in a few seconds.
Thanks. So the question is, do you already use virtual simulation tools for product development processes in your department? And it would be great if you could answer that question, so we have an overview on our audience today. Where are you standing in that process, so to say?
So I would close the poll now. It's so we have like 67% yes and 33% no. I will give back to you, Mike.
Yeah, thanks, and thanks for answering the question. And it's 2/3 and 1/3. So most of you are already using virtual development, which is not really a surprise. Thank you for answering the question. And please, Alfred, it's your turn now. I will make you give you keyboard and mouse control, so you should be able to switch the slides now.
Okay, so a few remarks maybe about the things that Michael has been talking about. You have seen I would say really kind of a disruptive change in the development of audio systems for automotive applications because of two things. I mean, one thing is we're extremely front loading, so we're moving more and more technology into the pre-development and concept phase. And at the same time, clearly, it's a simulation-driven approach. It's not uncommon to do this in the automotive industry, but it's really quite new for audio systems. And I believe this is simply because of the role of audio systems is simply becoming more and more important, as Michael pointed out. So I will not focus here so much really on simulation technology because I think it's there. It's available. We have really mature tools. I mean, I'm working on automotive audio since 2006 and on multi-physics simulation since the early 90s. I mean, in the 90s, it was really research and thinking about maturity of available software technology and simulation tools. That's not the point anymore today. The tools are here, and I think Mats has given you a good introduction. What is really possible? The challenge is really what to do with this in a large organization. I mean, if you develop a car today, this is not straightforward. You really have to orchestrate many engineers, and if you look at the feature list of a car, it's unbelievable what features are important. At the same time, that's all changing now. We have totally different requirements now, because the role of a car might even change. And I'm not talking only here about electrical vehicles and autonomous driving, which might be another change. So I would really like to spend some thoughts here about what I see a more challenging situation today, not solving the physics, the multi-physics, but really how can we integrate that and roll it out internally in a large organization. And here are some thoughts from a technical point of view. First, what are the challenges here, and where do you as a user or as a possible user need to look at? And then also from an organizational point of view, which I think is also very interesting. And also because, you know, in the past, a loudspeaker or an electromagnetic transducer, he was treated as a component simply. It's an electrical component, but there's a very strong interaction between this component and the car itself, the car cabin in an acoustical and also in a structural way. And that really makes it challenging. You cannot simply, you know, source a loudspeaker from a supplier. You source a wonderful loudspeaker and you put it into a car, and it's totally different, the behavior then. So we really need to understand the application here. So, I mean, this is our tier level paradigm here. You know, it's I would say physics or technology driven. We look at the main component, of course. That's the starting point. We want to reproduce audio in a car cabin, and for sure we need to look at the transducer. And then we have, you know, with level 2 and 3, really this strong interaction with the car structure, but also with the acoustical cavities that we have in a car. There are many. I mean, you need to mount the loudspeaker somewhere, and often, you know, a door is, for example, used as an enclosure. That's not a good enclosure, really. You really need to understand what happens with the interaction. Then, how does it degrade the performance of the speaker? And then finally, I mean, we have all the speakers, and today we really talk about many speakers in a car. We talk about immersive audio. So I mean, really, it's not a radio with a few speakers, or maybe only 2 speakers in it. I mean, that goes up to, I think, 34 or maybe even 38, what I've heard. And that opens a totally different scenario now. And then what we believe also is very important to look at the electrical domain. I mean, you do not simply put loudspeakers into a car and then you apply voltage and reproduce sound. There's a lot of tuning, which is really, I mean, I would say optimizing on signal processing level, the output of the speaker, that you have a really pleasant audio reproduction here, and that needs to be checked. So it's not something that you can define by number. You really need to listen to it, and that is why we actually introduced these realizations already in the early phase. Because as Michael has shown you, I mean, if you would look at the real time scale, we're still talking about a timeline of 3 to 5 years for developing a car. So it takes a lot of time. And you define a concept, and then maybe 3 years later, you might have the opportunity to listen to it and figure out, oh, we have a problem. So that is why I'm talking about front loading. I mean, really do the things in the early phase. So what does that mean for the software? Well, first off, let's look at the. I'm gonna start with tier level 1 here, the loudspeaker, the transducer. Looking at it's a multi-physical device. Everything is strongly coupled. We have West electromagnetics and structural dynamics. The membrane is actually moving the air. That is what we're listening to then. And then we have the acoustics that really propagates the sound waves. So what does that mean to the simulation tools? Well, it depends what your role is. I mean, for the supplier of the transducer, it might be a little bit different than for the OEM. For one reason, and that is because the supplier, he has to really work on the design and ultimately optimize the design of all the components and subcomponents of a loudspeaker. not so much for the OEM. So I mean, he would simply source the speaker, but his responsibility then is really the integration, and that makes it a little bit challenging, as we will see later, in terms of the mechanical and acoustical integration. So there are different requirements, so that the supplier might need more details, and he really has to model especially the electromagnetics on a very detailed level so that he can optimize it, especially because you need to understand that we look at the cost structure of a loudspeaker. 80% might come from the motor system where we have the electromagnetics. So this is one aspect that you need to understand, and then also later I'll talk a few words about, you know, the interaction between the supplier and the OEM might also have an impact on this here. The other thing is we have two approaches in multiphysics. One approach is like Comsol does it, to use an all-in-one solution. So that means all physics is there. And I think this is one of the reasons why you can really treat Comsol as an industry standard tool for loudspeaker development, because as a loudspeaker developer, you need to look at the electromagnetics. You really need to look at the details of your subcomponents, not only the motor system, but also the membrane. We might have, you know, effects that are acoustically challenging and not really nice for reproducing sound like a so-called rocking mode here. And that's nice if you have it in an integrated environment. But sometimes you might prefer code coupling because for some historical reasons, you might already have some solutions or models and you would like to reuse them. Then the other approach is really going for a code coupling thing. And that makes it really challenging if we're talking about three different physical domains, because three different tools might be involved, and data exchange is a challenge. And then you also need to have, you know, a compatible revision of all the different tools that you're using here. More or less the same thing applies if we step up to level 2, looking at the integration of the loudspeaker. I mean, that has a strong impact, of course, on the vibrations of the membrane and the sound radiation. In automotive, we have some really specific challenges. I mean, extremely complex geometry of enclosures. As I mentioned, we use a door as an enclosure, which is not ideal, of course, because it's quite shallow and it's soft also, so it vibrates as well and might really destroy the performance here. And I mean, interior design always would like to hide loudspeakers, so that means we're using loudspeaker grills to make them invisible, and that also has a severe impact on the audio performance. And that's a different story now here in terms of physics, because we're coupling different domains here. We will end up in a multi-scale problem, because on one side, talking about the motor structure, you know, we have very, very thin geometries between the voice coil and the magnet of maybe 0.5 millimeters or so, and then we have a door 1 meter, or even the whole cabin. Later on, it is a couple of meters, and here it's a really challenge. But it's the same situation here for the tier 1 supplier and the OEM. They have to use reduced models. I mean, reduced models in terms of the level of details, because otherwise you would really have an explosion in the capacity of your computer that you would use here. So here they are more or less on the same thing. It's a crossover thing. Who is doing what? I mean, the OEM has the advantage that he has access to all the information regarding the car, and that might be a challenge, of course, for the supplier then really working on it. Same thing again here. If we step up to level 3 now, I mean, looking into the cabin radiation, it's simply even more complex. You know, we have a more complex material mix with the interior acoustics and simply more components so we really need to look at the acoustical and the mechanical interaction that we have in that domain. Same thing I would say here really for the supplier and the OEM. What is really important here is to look at the role of NVH. I mean, there is a long tradition, of course, in the automotive industry to do acoustic simulations. So there are models already existing, and they might be reusable for audio simulations, because they model and simulate the cabin space, but not the loudspeaker. So in that case, I mean, it might be really interesting to use these NVH models and integrate the loudspeaker into the NVH model. And we really need to do a lot in terms of 1D, 3D coupling to bring in the electromagnetic equations. And that's a huge advantage because, I mean, it's more or less, you can do it easily to use these equation-based modeling in combination with very complex whole vehicle models here. So quick example here from our side here. What we do, so we simulate all the channels in a loudspeaker. We have a so-called localized sound power method to really measure sound inside the cabin. What I also want to point out here is audibility means always typically from 20 hertz to 20 kilohertz. So the typical approach in NVH using finite elements and the statistical energy analysis method for higher frequencies doesn't work here because we want to listen to the system, and the SCA that does a spatial average, so we miss the phase information and we have no chance for listening to it, and that really makes it unique, I would say, in terms of audio simulations, to use ray tracing so that we can really listen to the system here. I mean, these examples here, it looks fairly simple. It's one of our trainings examples. Unfortunately, we cannot show any real-life customer applications here. But the thing is, it really, if you want to listen to it, it also means you need to apply signal processing and tune the system. You know, we have constraints in the location of loudspeakers, means different arrival times of sound waves. Distance also means different levels, and we need to apply cues, especially at lower frequencies, to apply for or account for modal effects where we have resonances, where we can have peaks and notches in the frequency response, and finally we can listen to it. So that is really important, I would say, that we can listen to the concept in the early phase already to say, well, is it a good concept or a bad concept? And I mean, I'm gonna not really talk about that. And of course, we need a measurement system, even if we're all talking about, you know, in the extreme case, physical prototype-free development. It actually means we want to push back many of the early prototypes because they're not really relevant in terms of the acoustic performance. And then ultimately, in more or less the same step, we'd like to validate the design and the simulation. So from an organizational point of view, what does it mean? I mean, Michael talked about the digital reference. It's great that we can assess, you know, the concept or the performance of the concept by listening tests in such an early phase. But the organization need to be ready for that, because we might then figure out, hey, we have an issue here, we need to make some changes. But what I see sometimes, or actually really often, is if you're not prepared for it, there is no room, there's no time left over that you do any changes because you couldn't do it so far. And I mean, going further then in the development and really adding details for the digital twin, I mean, what the really interesting thing is that we can look at the degradation that we have done because of all the design constraints. I mean, the digital reference is an ideal situation where we say, well, that would be the best thing that we can achieve with this number of loudspeakers, this type of loudspeakers. But then, of course, you have not only design constraints, but also cost constraints. And that's also a thing, you know, that the organization needs to be prepared for, because now you can really have constant reviews of the performance degradation and say, hey, hold on, now we do not, that really doesn't match with our performance targets that we are looking at. And also, I mean, everything is pushed forward. So the question is also, do we really need these early physical prototypes? And I say no, but what we need are virtual prototypes from suppliers. So they shall deliver a virtual prototype for the simulation model to be used in the digital twin, not the physical sample, which really can be done later. Well, external effects here on the supplier side, what does that mean? Well, I mean, you have the chance to, you know, if you push your supplier to work on innovations and maybe also disruptive technologies, you can really assess them virtually in the application. but then you need to be aware, well, it's a very early design phase. And do you really want to involve your supplier here? What does that mean in terms of IP and compliance? This is simply new. Usually you wouldn't do this. So you would really see then your supplier in a new role as a provider of technology and as a technology partner. So that is also something that is very, very interesting. So that role, I think, needs to be changed if we want to have even more benefits out of this digitalization approach here. And as I mentioned, suppliers, and we see this in a couple of other applications in the automotive industry, they shall deliver virtual prototypes as early as possible, that you can really assess them in the application. And that also means that, you know, once you do the tuning work, that is typically done in the, I'm not so sure about the C sample phase, because acoustically most of the parts might not be ready in such prototypes, but in the D sample phase, you can actually start with the tuning work earlier and with the ultimate assessment of the quality. But that also is something, you know, that you need to account for in the organization, if it's doable. And then you need to define the steps, and really involve the people at the right time. And that's most of the work, I would say, that we're doing at the moment. Not so much looking at the physics, but really looking at the organizational aspects by introducing this new technology. That's it from my or our side, from Michael's and my side here. What we do at the moment within the automotive industry, with focus on acoustics and audio.
Oh, sorry. Okay. Thank you very much, Alfred and Michael and Mats, for your contributions here to this event. And as already mentioned, we will have now Q&A session, and we received some questions, and I would like to motivate the audience to still feel free to ask your questions. It's possible to do that, and we will see how many of them we will be able to answer. So let me now just find the questions section here. Here we go. And the first question maybe is for the Android people. Due to the digital transformation in general in the automotive industry, there are already many changes going on, and how easy is it to integrate Android into existing and probably changing processes? Is there a requirement for new interfaces, and what CAD systems can be connected and so on? Can you comment on that?
I will probably start with it from a technical point of view, because, you know, CAD system, that's always a challenge, I would say. Technically, it's not so much the challenge. I mean, as long as you know, finite elements exist, there exists this discussion about CAD interfacing. But the role of CAD is changing now. I mean, if you look at the simulation-driven design approach, you use a CAD system not as a documentation tool to describe your design. It's really a geometry modeler within a functional markup where you describe the performance of your system. That's not really a big deal today, I would say. I mean, you know, there are major platforms. There have been a lot of market concentration over the last 2 decades. I don't really see that as an issue. I mean, it's a little bit an issue with the different simulation tools, but we have a mesh compatibility here, so that kind of an industry standard mesh definition can be used through all the tools, which is fully supported by Comsol, and we don't really see any issue docking on other tools. That's all done, but I think it's really more the organization that might have a challenge introducing our technology as a whole. You really need to look at your development process, how to integrate it from an organizational point of view. I mean, you need to write it down. I mean, maybe Michael, you want to add some words to it?
No, I absolutely agree. It is, at the end of the day, we are completely in line with, I would like to say, from process-wise, looking at the different steps towards the conventional process which is existing today. But we all know what does it mean really changing a process, an existing process, and this is one of the biggest challenge at the customer side, and this is really independent, I would like even to say, from the tool, where again, what Alfred said, we are completely really in line with existing tools like Comsol, so that no major changes, adaptation are required.
Okay, thanks. And then we have a little bit more practical question concerning here the simulation part. One of the attendees aim is to optimize speaker placement to counter low frequency problems. Is that possible with Comsol? And is there some kind of a demonstration? If so, to demonstrate that there's a method to do that in Comsol. Mats, can you comment on that?
Well, yes, it's possible. I think, Alfred, you would agree also. I think a good place to start could be, yeah, I'm just sharing my screen. I'll just show we have a little tutorial, which is you can find on our homepage. It's called Car Cabin Acoustics. You search in the search field up here. It's a model of a car cabin, very simple geometry, some generic geometry, and then we do in this model there's both a frequency response done up to 1 kilohertz, but we also do a modal analysis. So you can monitor, look at the sound pressure level distribution, the sound pressure level at the seats for various frequencies, look at the response in an array of microphones. So I think this is probably the first place to start, and also especially I think for low frequency issues. So correct me if I'm wrong, Alfred. One good thing is to visualize the sound field, is to understand where are the, at the lower frequencies, where do we have the notches, when does the mode, how is the first mode building up, where is the notch in the sound field, how is that moving through the car as at the very low frequencies. So that can all be done.
And
maybe just a quick remark here. The question might also go in another direction in terms of active noise control.
Yes.
And that's another challenge here, I would say. That's even more complex. I mean, what we do here is we use Comsol results and then generate the summation and really try to control the sound field at low frequencies. And that is really what is, I would say, a very, very important application nowadays. Not so much entertainment. I mean, that is, I would say, quite natural to use loudspeakers as an entertainment system, but really focusing on the right comfort and trying to compensate noise by means of active noise control.
All right. Yeah, thanks. And then there's I like that comment. Auralization is impractically the proof that simulation works. Could you explain in more detail how is auralization validated and how does it work?
Yeah, well, I mean, that's actually straightforward to do the validation. Usually we do this with every customer. And I would say most of our customers are always curious about the whole audio system. And when we talk about the whole audio system, it is auralization, because simply showing you lots of curves, that doesn't help you. That doesn't really make sense here. But the ultimate validation is really sitting in the car. I mean, we are modeling an existing car in that case as a validation project. Listen with your headphones and then take off the headphones and listen to the real car. So we do a direct A/B comparison in the car. And
Right.
yes, it works. I mean,
obviously.
it's of course more challenging with the concept model because we describe an ideal situation, but I think it's also important that you trust the technology. So that is why we start always with, not with all customers. I mean, recently we've seen also customers that directly go to the application because they say, well, you guys, we know that's all working. That's all fine. We don't need the validation here of your technology. And they directly go into the application and start with a digital reference of a car line that is newly developed, which by the way is a really challenge at the moment because the whole structure is at the moment changing of a car because of electrification, and you might not have the typical places for your loudspeakers, and then you end up in a totally different result.
All right. We have a couple more questions, but we unfortunately run out of time. I think you will probably answer the questions afterwards, right? I think I can send you the questions. And great. So all of the questions will be answered. No worries, but we're running out of time, so we have to stop here. I'm afraid. So. Thank you, everyone, for your kind attention. That was really a pleasure for me, and was a great webinar. Thanks to the speakers here, and yeah, hopefully see you again in another webinar or for another event in the future. So goodbye and have a great day.
Thank you. Thank you very much.
Bye bye.